Yes, good afternoon, ladies and gentlemen. It's a big pleasure to be here. I will give you an overview about what robotics can do for space and for planetary, or for terrestrial applications, actually. And our main motivation are, of course, missions in space, and here we focus on mainly three application areas. One is on-orbit servicing. It means the capability to grasp satellites which are not operative anymore and repair those satellites or extend their capability of operation. Then assisting astronauts in their daily work. And the third topic is planetary exploration, so exploration of Mars, Moon, or other bodies of the solar system. But the nice thing about robotics is that these basic technologies we develop here, you can apply also to many applications on Earth. For example, there's a one-to-one link between orbital servicing and future manufacturing industry 4.0, or space robot assistance and medical healthcare assistance, or even robots for future domestic applications. And then the third link between planetary exploration and field robotics, that means application in search and rescue environments, in managing a crisis on Earth. So I will start with the first application, and as I mentioned, the first one is using robotics to do servicing in orbit. Space is quite expensive, partly to the fact that satellites are designed for 20 or more years of operation, while having robots which can repair serving those satellites can reduce costs and also increase flexibility of space operation. And robotics provides a quite scalable technology which you can use for simple repair applications, but also for building up large structures. And therefore, we developed over the years robotic arms, robotics technology, what we call soft robotics, so robots which are able to interact with the environment. And currently, we apply this technology, so the arms and the hands, in missions in which we try to demonstrate that indeed there's a business case in servicing satellites. And there's a large mission in the US managed by DARPA where we are providing the robotic hand, but we are still pushing forward for our own European or German mission where we show that with a lightweight arm placed on a satellite, you can grasp other satellites, lock them, and then release the arm to do some other operations like here refueling or servicing of general type. Now, in order to develop this new kind of robotics, actually we had a long-term program at DLR. We started about 20 years ago on the development of lightweight arms and then hands, and then continuously increased the complexity of those structures up to humanoids, wheel-based humanoids, or humanoids on legs. And there has been a continuous increase in performance in robotics, still being far away from what humans can do nowadays. So we have, especially in mechatronics, control, very strong advances. On the artificial intelligence side, there is still big progress to be made. But on the other side, you know, compared to the 4 million years evolution for humans, I think we are progressing pretty well. So what do we need? What do we mean by compliant robots? Classical robots are big, large, and rigid, pretty dangerous. And at DLR, we started a change of paradigm towards lightweight, compliant, and adaptable. Compliant means that by software, you can program the stiffness of the system in each space direction and also the damping. And you have a robot which can easily interact with humans. And most important, you can show that these robots are not dangerous to humans. If you know about Asimov's first law, of course, everybody is so concerned about the danger from the humans. We can demonstrate that these robots can be easily operated. Now, how can you use this relatively abstract concept of compliance to do applications? First of all, what means programmable compliance? You have a robot which has some desired forces and positions, and what we are particularly developing are sensing capabilities which closely mimic the potential of the human muscle. So we measure position, velocity, but also torques in each joint, and by using advanced control methods, we can shape the stiffness, damping, and inertia of the systems to apply it to the task. What does this mean? Imagine you want to grasp an object. Then what we do is attaching some virtual springs between the fingertips and the middle of the object, and another virtual spring would pull on the object. In this way, when you pull on one of these springs, all the finger springs basically will grasp strong on the object, and naturally the grasp force will increase proportional to the movement velocity. And now you can generalize this concept to more and more complicated tasks. So for 2 arms, 2 hands, for manipulating even complex objects like demonstrating juggling and so on. Of course, you don't have these virtual springs in reality, but you have motors in each joint. Some of those robots have 50 or even 100 motors. So the way we move those motors is that we take the potential of these virtual springs, do a partial derivative with respect to the generalized coordinates, and generate torques, and then compensate for gravity and some damping. These are technical details, but I think the main idea of those virtual springs is the way you should think about those robots moving. Now, of course, this is the mechatronic and control level, but you would like those robots to do some useful general task, and I deliberately have chosen something which is familiar to everybody, not a space application, but a robot cleaning in a household environment. So now we have to imagine that we have to control all these virtual springs in such a way that the robot does something meaningful. And the question is how to program all those robots. You don't want a PhD student to go to each of those springs and adjust for each task, but you would like actually to do a parameterization by learning from examples, from experiences. So you would start programming by hand, but then using big data analysis technology to see how humans have programmed that and generalize tasks or generate quite general applications in which the robot could do such different tasks like wiping a table, cleaning a mug, or cleaning the floor by just adjusting those parameters automatically. Now, one essential issue which I addressed at the beginning is safety. And we licensed this technology to an industrial manufacturer, to the company KUKA, but the third thing they asked us is, can you ensure that even in case of failure of sensors, your robot will not harm a person? And if you know about industrial robotics in car manufacturing, they look like this. They are big, heavy, they have to stay behind cages because they are very performant but dangerous. So we started, on the way to commercialize those robots, started looking at the way the car industry is ensuring safety of their cars, and they are using crash test dummies and defining different criteria. So we started doing the same thing in robotics. We were the first group to start doing these things, and after about 6-7 years of research, basically we were able to massively influence the ISO standard, which now regulates the way robots have to be built and controlled in order to be safe for humans, and we could prove that using certain set of parameters, you will always stay safe. Now, in order to do that, we did a lot of experimental work, and we started indeed with crash test dummies, but then we found out that the way of interaction is very, very complex, even more complex than the accidents you can have in cars. So you can have sharp tools, you can have knives, and so on. And we succeeded to demonstrate that by using this torque sensing, you can really stop the robot from colliding and being safe under a large set of applications. And well, this kind of self-experiment, this is a PhD student, which now is a professor in Hanover. So he did not have any damage either. But if you do something like that, you got interviewed by Discovery Channel and CNN, and you get a lot of publicity. Anyways, he did all those experiments 3 years before, so he was very confident on what he was doing. Okay, how can one imagine using those robots in human interaction? Of course, you don't need only robots which are safe, but you need an intuitive interaction. You need cameras, you need recognition of voice, of gestures, but you would like also to recognize haptic gestures. So you would like to interact with the robot in a very natural manner, in a way you would interact with humans. At any time, you can stop the robot, push it back on the trajectory. Even pulling hard, you can stop it in its action, hang it in a virtual field, then correct what it has to be corrected, and then resume the activity. So the question is, we had a research project now funded by Helmholtz where we try to generalize the concept which was so successful in smartphones on having apps which are developed by a large community, distributed by a cloud-based distribution system, and which atomizes the actions of the robots to provide a functional, very rich set of behaviors. So generalizing this to robots. So the basic question is, what are the apps for the robots such that anybody can program a robot and does not need to be a computer science expert? And actually now we have a spin-off company which came out this year at the Hanover Fair with a commercial version of this robot. And 10 years ago, as mentioned, it was prohibited to have robots interacting with humans because nobody knew about safety. Now it is a standard, and this was one of the hypes on the Hanover Fair in robotics. And the leader was KUKA, a company which licensed this technology from DLR. This is the commercial product from KUKA. This is our prototype. And then all major manufacturers followed. The problem is that the systems are still quite expensive, are about $100,000. And now our spin-off company came out with a robot which is in the range of 10 kilo euros. So basically, they want to enter mass production of this kind of interactive robots, which would be a very big step forward. Okay, but coming back now to our space applications, how can we use those robots to do servicing in space? Well, there are two approaches. One is autonomous operation if tasks are simple and you have very good image processes and artificial intelligence. But the most intuitive way is to have a human teleoperating, if you want to call it so, robotic avatar. So what happens is that the operator sees the 3D image using a hand-mounted display. So he sees the image which is gathered by the stereo camera of the robot. And when he commands the arms, he will also feel the interaction forces. So he will feel if a screw is jamming, or he would feel how strong he will push when assembling a part. And this can be done over distances where you have time delays below 1 second. So basically, with a good internet connection, you can operate a robot on any point on Earth, and with a good radio connection, we can operate robots in space. And we demonstrated that in a scenario of operating robots on planetary surface. NASA has a big goal to go to Mars in 2030, 2035, but in the first stage, they won't land because it is much too expensive. But they would operate with little time delay from the orbit robots at different locations on the planet. And we built up the infrastructure to demonstrate this operation facility together with Russian astronauts last year. So we had force feedback joystick on the ISS, and one operator being in Russia, the other operator being the cosmonaut, and they together operated a robot. We did a lot of psychophysical experiments to assess the way operation changes in zero gravity, but also we had a very interesting public outreach event in which we invited also the wife of the astronaut, which could not only hear and speak to him, but also shake hands, and we had also other people interacting with the robot. Basically, we wanted to demonstrate that teleoperation is feasible today as soon as you have a fast internet connection. This year, we will demonstrate the same technology on a higher level, so the astronauts will now use tablet PC, which is even more familiar to them, to trigger high-level actions for maintaining a large infrastructure like a power plant on a planet. The last maybe 2 minutes I would like to spend on the topic of exploration. And what we are doing today, or NASA is very strong, JPL in doing that, exploring Mars in rather flat terrains, while geologically it's even more interesting to go there where you have steep terrain, hardly accessible terrain, because there are geological features which are the exciting ones on the search for evidences of past life. Now, we would like to develop robots which are able to handle this unstructured terrain in an autonomous way, because remember, you have about 20 minutes time delay from here to Mars and back, or even more. So this is an example. This was a German competition last year in which so the competitors had a very rough information of the terrain, the kind of information you would have from a satellite, and the robot had to rely on its cameras and autonomously build a map of the environment, navigate in this environment, localize some objects, in this case a can with with soil probe, and then there was another object behind. The position of those objects were unknown, and the object grasped those objects, the robot grasped those objects and brought them back to the base. So this is the level of autonomy we can do right now. It's not a level of autonomy used in planetary applications, but this is the future towards which we will go step by step. And in order to validate this technology, we have, again, a Helmholtz project called ROBEX, working together also with institutes working in deep space and in underwater. And last week, we had a campaign in which we demonstrated and evaluated this technology on the Etna volcano, which is an analog to the lunar environment. Finally, I would like to point out again that also this mobile technology can be easily applied on Earth. For example, this mobility of the rovers led to some prototypes of autonomous vehicles which we call robot cars, which are able to turn in place, to park to the side, so each wheel is controlled independently, while the image processing we developed for display and analysis of the Mars data has been licensed and used by Daimler in their collision avoidance and reaction technology used in the Daimler cars. Okay, so I would like to summarize by pointing out, I hope that I could give you a brief overview on our robotics activities. And the exciting thing about robotics is that on one side, we can contribute technologically to understanding the universe by exploring bodies of the solar system, but also by maintaining space infrastructure. But there's a further motivation behind robotics. And this is to understand and replicate in a different way than human sciences are doing the capabilities of the human, in a constructivistic way, in the sense that we are trying to really understand by rebuilding those functionalities, rather on the functional than on a cellular biological level. And on the third level, we are addressing major societal challenges like healthcare, aging society, and industrial competitiveness, Industry 4.0. Thank you very much for your attention.